Hello, we are the Clemson University team presenting on the BESS optimization peak load shaving. Our team consists of me, Cameron Cromer, Bryce Carter, Sienna Dushnek, Justin Goodman, Michael Marinaccio, and Tong Vong. Our project consists of the hot spring microgrid BESS system, which was the 1.8 megawatt PV plant in North Carolina, which was interconnected with the Marshall Hydroelectric Plant, but the POI connects to the same transformer as the breaker from the dam. Our BESS system is 4.4 megawatt hours with a lifetime of 25 years. The battery SoC is monitored by SCADA. The BESS should help with attaining peak load shaving, PV smoothing, energy arbitrage, and frequency regulation.
Our goal for this project was to develop control algorithms to predict the target state of charge and load profile of BESS system at a microgrid PV plant in order to preserve the longevity of the BESS. So what this meant was developing a BESS load profile and target SoC algorithm to economically utilize BESS to reduce peak generation requirements while maintaining warranty ranges and reliability standards, and also to develop a machine learning prediction algorithm that's trained on past data to accurately predict circuit load, PV generation, and peak hours. Taking a look at our motivation and constraints. So our motivation for this project was first, the utility adoption of grid-scale lithium-ion battery systems. As renewable energy sources are more interconnected in our system, we need batteries to support them, so they're becoming more adopted. Also, lithium-ion cell degradation factors like charge cycles and high state of charge. We want to find an optimal charging profile to balance the battery life with cost savings and meet energy reliability metrics, that being a 97% availability by Duke standards, and to maintain circuit health. And also our constraints, we wanted to have as lightweight operation as possible for the hardware that we're working with, an Ubuntu Python environment, and charging limitations to stay within the battery warranty.
This is just a quick overview of what our block diagram is looking like, and we'll be going through this as we continue on with this PowerPoint.
Here's an updated look of the GUI. On the left side, you can see just the base landing page of the GUI. The top middle is a graph of historical data. The top right is an output of our charge profile algorithm. The bottom section is just the date selection and an error message that occurs when you select an invalid date. And the functionality of this will be covered fully in the demo at the end.
To go over what type of machine learning we use logistic regression on things that work with ranges. So anywhere between like 0 to 100, where compared to and k nearest neighbor when we're working with continuous value, which is any type of number, including decimals. The reason we worked with these two is when we compared to KNN during one of our outputs, logistic regression performed way better compared to k nearest neighbor and linear regression. And when we were working with continuous values, k nearest neighbor performed better than linear regression. One thing that we did have to work with when we got our data set was due to blanks happening be in the Excel file, we had to fill those in. And the way we did that was using simple imputer. This allowed us to fill these blanks in the cells with whatever we thought was best fitted. So if we were looking at solar energy and we realized all the blanks were happening during the nighttime, we can fill those in with zeros. And if we looked at blanks and it was surrounded by ones, we can fill all the blanks with one. Another thing we did was we had to drop out columns that did not provide relevant data. If we were looking at the same station throughout the entire data set, we would want to remove the stations because that doesn't provide us any useful data. Another thing that we did was we changed all of our data to numerical. So if we had a category data like cloudy, rainy, or snowy, we would change that to 1, 2, 3, and so on and so on. Most machine learning does this, which is we split our data to 80% training and 20% testing, meaning we train on 80% and then using that, we created the algorithm and then tested it on a 20% set of the data.
Here are our results for our 3 metrics that we were predicting: severe risk, PCC, and BPN. For severe risk, we used logistic regression, and for BPN and PCC, we used our k nearest neighbor, and the scores are seen below.
So we had 2 algorithms that the machine learning were inputs for. So the first one was target state of charge, where it chose between 4 risk levels and then would output the actual state of charge that the battery should be at keeping in mind the limits of being above 20% and below the 90%. It also considered the likelihood of an outage. The second algorithm is for the charge profile, where it determines the mode of the battery and also the actual percentage comparing to the target state of charge. And this considers the inputs of the likelihood of an outage and also the generation of the PV plant and the load that is required.
Some of the strengths for the design of this project are the fact that the code of the updated algorithms and the new algorithms is easier to understand than the previous versions, and the computation time is quite quick. Some of the weaknesses that we have are that we had to test with limited and incomplete data sets, and we had to predict for hourly data, and also had to split up data that had minute-by-minute data. We had to split up into 3 different subsets of data depending on the output, because we only had 2 months of good data for solar generation, 8 months of data for severe risk, and 2.5 years of data for the actual weather data. And a general summary of the semester, we started off conducting literature reviews to gain an understanding of BESS storage systems and machine learning techniques. We developed the machine learning algorithm for load and PV generation. We simulated prediction and control algorithm integration. We updated the GUI, target SOC, and charge profile algorithms from the previous semester. And the future improvements and next steps for the project include improving the prediction algorithms by using more historical data as more data is available, incorporating the algorithms with the SEL 3350, and we'd have to modify the algorithms in GUI to integrate this further, and then testing the implementation of the project with real-time data. Now for the demo of the GUI. When you run the Jupyter Notebook, the GUI appears. You can click Feeder Data to look at the historical data of the circuit, the kilowatts, kVA, kVAR, current, and voltage. If you select the actual circuit kilowatts, you can get a date selection menu, where you can select a date such as February 6th. When you select the date, then the historical data for that date will appear. If you select a date that doesn't exist, such as February 30th, an error message will appear. If you select a date such as November 30th, which does not have data for it, then an NP graph will be populated. The 2 main algorithms used in this project, the target SOC and charge profile, both interface with the machine learning algorithms. When the target SOC algorithm is run, it outputs a 24-hour prediction of the hourly risk level for severe weather, and then outputs a designated target SOC depending on that risk level. The hourly risk level is determined based on the severe risk variable outputted by the machine learning algorithms. The charge profile algorithm simulates 24 hours of what the battery's charge should be. There are 3 modes of the battery: discharging, idling, and charging. And the corresponding charge level is outputted in the right column. The mode of the battery, whether it be discharge, idling, or charging, is determined based on the load of the circuit, the generation of the PV on the circuit, and whether it is above or below the target SOC, or if it's reaching the minimum threshold of 20% charge. That is the demo of our GUI. Thank you.